has 3 ones. And this is necessary because each node in the graph has 3 neighbors, right? So a quick check to see if this is somewhat correct is to check if you have 3 ones in each row. Yeah, let me know if you have found something else, and we can discuss later. Yes, okay. So here's the adjacency matrix for graph C. Again, nothing too fancy going on. You see that this node 8 down here, it has no neighbors. So all of these elements is 0 in its row. And the same up here, everything is 0. All right, and let's look at the adjacency list. We have here the graph A again. And yeah, just as shown in the slides, you just make an array here with all the nodes. And then you have a linked list connected to said array on each element. So for example, node 0 says here it's connected to 1. Yeah, okay, that's true. It's connected to 4 and 5 and so on, as you can see. Again, each node has 3 neighbors, so there should be 3 elements in each of these linked lists. Yeah, and then you can just walk through it and see what's going on. So yeah. And here we have the adjacency list for graph C. Again, nothing too fancy. You see that number 8 down here. He's very lonely. He has no linked list. That corresponds to him having no neighbors, which is true. So yeah, just simple adjacency list and adjacency matrices. Now we have to simulate a BFS on our graph A, starting in vertex 0, which is the one on the top here. And we assume that the adjacency lists are sorted, and that's important for which direction we expand towards. And then finally, we have to specify the BFS tree, the DFS tree, and discovery and finish its times. And please, everybody mute yourself. If you're not asking any questions, please mute yourself. Thank you. So let's look at what happens here, right? So we meet vertex 0, and then we give a discovery time of 0. This can also be 1, but I've just chosen to go with the 0 indexing here. And then we look at his neighbors, right? We have 4, we have 5, and we have 1. And now it's important that the adjacency lists are sorted. So the first neighbor we will select is always the neighbor with the lowest value, in this case, the 1, right? So we make a line here, and we visit node 1. And now he has a discovery time of 1 because we had a discovery time of 0 over here. Yeah, and we just continue moving on. Now at node 1, we have neighbor 6 and neighbor 2. We also have neighbor 0, but 0 is already visited, so we don't go back here. And now we select number 2 because 2 is smaller than 6. So yeah, and obviously now discovery time of 2 is 2, and we just continue moving on in the same fashion here, as you see. Now we reach node 4, we have 2 neighbors. We still have 3 neighbors, of course, but 9 is the only one which is unvisited. So we go over to 9, and 9 has discovery time of 5, and we simply keep going through the star here. And at some point we reach the node 7, right? And when we're in 7, if you look at 7's neighbors, we see that they are all visited before, right? We have seen 5 before, we have seen 9, and we have seen 2. How do I know they are visited? Well, you can see I've written a discovery time. That's pretty simple. So that's how we know that they have been visited. So now we start backtracking, right? So we go back to node 5 here, and in node 7, we know node 7 is finished. So we write 10 here as the finish time. So we have to start backtracking a little bit. We go up to node 5 here, In node 5, we see that all his neighbors are visited again. You know, we have seen this before, we have seen this before, and we have seen the 7 before, obviously. So we backtrack furtherly, and we write finish time 11. And actually, all nodes here have now been visited. So we simply backtrack through the way that we discovered stuff, and we end up by having this final BFS tree, if that makes sense. And you can see the start and the finish times, or the discovery times, is this brownish color, and the finish times is the blue color here. And so the BFS tree will simply just be, you know, follow these edges around here, like so. And if you were to put all these edges in a row, if you just follow them, you'll end up with like a long line of nodes hanging together. But yeah, you can try that out for yourself. All right, next question. We have to show BFS now on this graph A, and we are starting in vertex 0 again. Again, we assume that the adjacency lists are sorted, and we specify the BFS tree and the distance for each vertex. So let's start. Let's see what happens here. We start on node 0, and he obviously has the distance 0 to himself, right? That makes sense. And then we look at each neighbor. This is a BFS we're running. So remember, we look at each neighbor. We mark each neighbor like so. They all have distance 1, because it's you know, the distance of the parent plus 1. So yeah, it's they all have distance 1, obviously. And now we have to choose a node where we're going to do the next expansion, right? We have to choose a node among these nodes here. And since the adjacency lists are sorted, we choose node 1, which is over here. So let's see what happens in node 1. He meets 2 new friends here. He meets node 6 and node 2. And here we just write 2 and 2. Oh, and I just realized that I'm calling these circles nodes, but in the lecture, I think Philip is calling them vertices. Sorry about that confusion. Nodes and vertices are the same thing. I will try to remember to call them vertices now, just so that you are not confused. But it's basically the same thing. All right. So what happened in vertex 1? Well, he has 2 neighbors. So he has vertex 6 as a neighbor and vertex 2. And we give both of these a distance again. And now we're done with vertex 1. We move on to the 2 other vertices we have here of the same distance as vertex 1. And we select 4 to expand from, because, you know, the adjacency lists are sorted and 4 is smaller than 5. So let's see what happens at vertex 4. Well, he meets vertex 9 and he meets vertex 3. And again, we give both of these a distance. And now we are left with one vertex 5, which has this distance 1. So we shall also expand on this guy. And he meets vertex 8 and vertex 7, and we give both of these a distance. And so now we're actually finished, because now we look at each vertex with distance 2, and we start with vertex 2 down here. Well, his neighbors are already visited, so we cannot expand further from this vertex. The same holds for vertex 3, holds for vertex 8, 7, 6, and 9. So now we're actually finished. And as you can see, these distances are correct, I believe. Yeah. And the BFS tree is simply the tree where you follow these orange or brown lines down. So that will be the BFS tree. All right, let's move on a little bit here. now we have to specify the connected components of graph A, B, and C. And if you recall what a connected component is, it's a set of, or a subset of vertices that are all connected, right? So in graph A, everything is connected. You have a fully connected graph, actually. So the whole thing is just a connected component. Similarly, in B, you have a connected component, which is just everything, because it's a fully connected graph again. And in C, we actually have some different components, right? We have this red guy over here, which consists of 4 vertices. We have an orange fellow over here, which consists of 5 vertices. And then we have our lonely vertex 8 down here, who's just chilling, and he's his own connected component. All right. So nothing too fancy. Again, just realize which components are connected and which are not. Now we have to show which of these graphs are bipartite. From your screencast, there's a lemma which says a graph G is bipartite if and only if all cycles in G have even length. That means that if we can find a cycle of uneven length, like in this graph A, we have a cycle here where there are, I think there are 5 edges or something. Yeah, and so that's an uneven cycle. Thus, this graph A must be not bipartite. Yeah, so this graph is not, and this graph over here is not, again, because we have an uneven length in a cycle here. And finally, C is bipartite as there's only one cycle and it contains 4 edges, right? That's pretty obvious from this drawing here, or from this graph, yeah. So C is bipartite, the others are not. And that's pretty simple to just see from this lemma here, and try to find uneven cycles. All right, so let's jump to this one. So exercise 2 is a implementation exercise, and I will show it in the end. The idea is that we use BFS to determine this distance between the start node and the finish node of the maze. And the steps in the implementation would be to create a graph from the letter maze, simply create a graph from the input that you get, and then implement a BFS algorithm and run this BFS algorithm on this graph here we have created from the maze. So I'll show that to you guys in the end. Let's move on here. Number 3, we have to use or we have to implement the DFS using a stack. If you recall from the lecture, is that they have made the DFS algorithm using recursion in the pseudocode they shown. But now we want to avoid this recursion and use a stack instead. So as the hint says, just use a stack. The idea is to simply copy the pseudocode from BFS, as I've kind of done here, and replace the queue data structure that they use with a stack data structure. So let's see how it looks over here. Well, we know this from the BFS pseudocode, just mark S, put the distance from S to be 0. And then here we use a stack instead of a queue. We push S onto the stack. And then we do like a while loop, repeat until stack is empty. We select the node V, which is the top element of the stack as we are doing a pop operation. And then for each unmarked neighbor U, for each unmarked neighbor that V has, we call U. And then we mark U, we give U a distance, we give U this pi thing here, and then we push u onto the stack again. And then you see that like it continues looping until your stack is empty, and then we are finished. So why does this work? So recall what stacks do, right? So you had about stacks last time. It's a data structure where the element you have put in will be the first one to be taken out if you haven't put anything else in, right? So like this last in, first out principle. And what does that mean if you apply it to a DFS? Well, that means when you're expanding through the tree or through a graph, when you meet some new neighbors, these will be put on the top of the stack. And then when you expand again, these neighbors will be the first ones to be expanded furtherly. If you're unclear why this works, I can try to show you an example or something where I draw the stack. Yeah, but sure, this is just, yeah, just use a stack instead of a queue and you are done, actually. Cool. Let's see what we have else.
Explain the UPy part. I know it's also in the original pseudocode.
Yeah. So I believe I believe u.py is a pointer towards the parent, right? So this guy here will be pointing towards the parent. And when I mean parent, that is like the guy we're expanding, or the vertex we're expanding at the moment. So you see here, V will then be pointed to by all the neighbors V has. Yeah. Let us. I hope that makes sense.
Yeah, it does. Thank you.
I don't know. Like I don't think I used it today. This pie here, but it's something so you can keep track of where you came from, actually. So yeah, you can leave it out or you can keep it in. It's up to you. Oh yeah. So let's see what happens here. We have to find a cycle and give an algorithm that determines if a graph is cyclic, which means it contains a cycle. And we have to explain how fast this algorithm is. So a simple idea is to run a BFS or DFS. If we, while executing, let's just say that we are going to do a BFS. While we are executing, if we meet a vertex which has been visited before, there must be a cycle. All right. So let me just show you. To the left, we have a simple graph, which is a tree. No cycles are here. I hope you can see that. So we start our BFS in node 1 over here. And we simply just go down here to 4. 4 is unmarked. So we mark 4. We meet 2, we meet 3, and we meet 5. And then we meet 6. All right. So did we meet any node here which has been previously met or visited? No, right? So 1, you haven't met that before. 4, you haven't met that before. 2, the same. 3, the same. 5 is the similar, and 6 is the same. Okay. So let's try over here on a graph which clearly contains a cycle and see what happens. We can start at 9 and run our BFS from 9, and we will expand towards these 3 guys or 3 vertices. And now we should expand from 10. Let's see what happens here. We go down, we meet 12, and we see that 12 has been visited before. So we know now that's a cycle. And this may be kind of vague on these, just like these 2 examples. So let's look at a general case. So assume you have some graph here in the middle, which contains some nodes and some edges, or sorry, some vertices and some edges. And let's say we start in node. I keep on calling it nodes, but I hope you get what I mean. Let's start in vertex S here. And we have a vertex U and a vertex V. And let's see what happens, right? So assume we are doing a BFS on this graph, right? So we start by expanding towards our 3 neighbors here. And at some point, vertex V will be reached. assuming that S and V are in the same connected component, you know, they are connected here at some point. Anyway, vertex V is met at some point down here. And similarly, that means that there must exist a path from S to V, right? Otherwise, we couldn't meet vertex V. Similar argument is given over here on vertex U. At some point, vertex U has been reached. That means a path from S to U exists. Let's see what happens now. Vertex U is trying to expand over here on vertex V. And that means, you know, since vertex V has already been visited, okay, we know that's a cycle, but since U can visit V, there must exist some path between U and V, right? So all in all, there's a cycle now, right? You go from S to U, you go from U to V, and finally you go from V to S. Okay, so it works in any generic graph or any graph at all. This cycle lemma here that we made. Yeah, so I think that's all the exercises. Let me just go back to exercise 2. Here you go. So recall that we are going to use a BFS to determine the distance in this maze. And the steps are that we're going to create a graph from the letter maze, which is the input. And as mentioned, we're going to run a BFS on said graph. All right, so let me show you guys how this is done. I hope, can you guys see my my code here? I believe you can. All right. So the first thing is that I've done it in Python and I've used some classes. I realized here the other day that some of you guys may not have been introduced to classes in Python, but I'll try to keep it simple and show you guys what the meaning is. Feel free to ask any questions about the program or the classes in itself and so on. And I've written the code, so it should be very easy to translate into Java code or C# code or any other programming language that implements classes. All right, so let's get into it. As mentioned, we want to create a graph from the input. And a graph, it must contain a vertex, right? So the first thing I do is create a class for the vertex. And the way I've done it is that the vertex, it has some position, and that is given by X and Y coordinates. And the vertex has some depth or distance. And initially the distance or the depth is none, right? We have not done anything with this node yet. And we have some neighbors for this vertex. And initially I'll have just made an empty list. So that means that it has no neighbors at the moment. And we have a letter. The letter, you know, we call that in the maze, that can be an A or that can be a B. So we assign the letter to the corresponding vertex. Okay, so basically a vertex class which contains some information, right? Now we have to create a graph class. And the graph, it must contain some vertices, a collection of vertices. And so how do I do this? Well, I call a method which is called graph, graph. And the input to this method is the maze. Okay. So how does this method work? Well, it takes input the maze, and we create something which is called a dictionary of vertices, as you can see here. A dictionary is basically a map, or yeah, you should have seen it maybe in some programming course. And if not, you can look it up real quickly. It's a really nice data structure. Anyway, so how do we create these vertices in the graph, right? So we loop over our maze, and we know the maze has length n times n. So we just use the length of the maze here. And then for each element in the maze, we create a vertex. So here we have the vertices map being appended by the position of a vertex, and the value of set position will be a vertex class, as you can see here. And how do we create this vertex class? Yeah, it needs a position X, it needs a position Y, and we need the letter of set element in the maze. And you can access this letter by just calling the element in the maze. All right, this may seem a little bit confusing. I unfortunately cannot share this code with you, but I can't do anything if you take some screenshots, right? So yeah. Now we have, as mentioned, created all our vertices, and these are now saved in our graph class. Now it's time to find these neighbors of each. Oh, sorry, can you mute yourself? Oh yeah, I've just done it. There you go. Now we have found the vertices in the maze. Nice. We have given each vertex a position, a letter, and a distance. Now it's time to create these neighbors for each vertex, right? To recall that initially the vertex has no neighbors here. So we should find out what neighbors each vertex has. And this is done in the find neighbors method, which is also called here. And the way I do this is that for each vertex in our dictionary of vertices, so this is basically a loop over all the vertices that I've created, I check the possible neighbors, which is basically just checking whether or not there is a neighbor in the north, the east, the west, and the south direction. And at most there can be 4 possible neighbors. So I've made, a list of 4 elements here. And then we check each of these neighbors in our possible neighbors list. If the neighbor is not none, that means, okay, there might be a neighbor. And is this neighbor vertex, has it the same letter as our, vertex we're looking at right now? And if they don't have the same letter, we know that it is a neighbor. So on the current vertex, his neighbors, we append, this neighbor the current neighbor we're looking at. And so slowly but surely, we are expanding this neighbor list up here. Yeah, and that's all you have to do for creating a graph from the input maze. I know it's actually kind of a lot of things you have to do. But yeah, so that's the way to do it. That was step 1. Now we have to make a BFS algorithm, which I have shown here. And this algorithm, I've just stolen it from the pseudocode. And an important thing to notice is that S, right, the vertex we start at, it is always located at the position 0.0 or 0,0, because it's always in the top left corner of the maze, right? that was one of the things that was given in the exercise description. So let us see here. As you know, we go in, we find the correct vertex, and here you can just put in this guy here. That means that you'll instantly access the top left vertex. I put the depth or the distance of S to be 1, and that's just something that that you must do. You know, I had 0 in one of my walkthroughs, but it must be 1, or otherwise it won't work. All right. So remember to do that. The Q, remember that I said that you can make a stack in the in the BFS you use a Q, obviously, and in Python you can call something called DQ. It's simply a Q data structure. Now recall from the pseudocode that initially you append the Q with S, and then while Q is not empty, you keep on popping from the Q. You keep on dequeuing from the Q. So that's what I'm doing here. While the Q is not empty, we grab some vertex from the Q, and for each neighbor that the vertex has, we first check, is this distance or the depth, is it none? Because if it is none, right, we set the depth to be none to start with. If it is none, we know that this guy, this neighbor, he has not been met yet. So we go in, we give him a distance, which equals our previous distance plus 1. And we put him into our queue. So this operation q.append, it's similar to a q.inQ. And this q.popleft, it's basically a DQ operation. So I can write it here, DQ and InQ, like so. And simply what this does, it gives each neighbor, or sorry, it gives each vertex some depth, which we are going to use when we find how long the distance is from the start vertex to the goal vertex. Whoa, that's a lot of talking. I hope you get the idea. 1, make a graph that can handle the input maze. Step 2, make a BFS. And now the final step here is to obviously load in the input. Recall that the first variable you're given is n, and you can just read it like so with this code. See, now I'll answer your question in a few minutes. I'll just do the just like finish this stuff up here. We have a maze matrix, which initially is just an empty list. And here is a smart trick to, you know, create this maze matrix, this code right here. And again, I'm not going to explain what these pieces do. You can just steal it if you want. Yeah. And then finally, we are going to create a graph called G. G is going to be a variable, which is a graph object, which is this class here. And the input obviously is the maze matrix, right? Then we use our G. We do we call the method of BFS, which is this guy here. And then in the end, we want to find the distance to our goal vertex, you know, the vertex in the bottom right of this maze here. Maybe I can just let me show you here. If you recall, this is what a maze looks like. And this is always the goal, and this is always the start position. So if we access the distance to this vertex down here, we know that the distance of this guy will be the whole path length from this guy to this guy. I hope that makes sense, but it may be a little bit confusing. Anyway, we had to access the right corner of the maze. And how do I do this? Well, I take my G variable, which is a graph, as I mentioned. We go into the vertices, and how do I find the right corner? Well, I know that the maze is n times n, so I just put this in as the position. And what this will return is a vertex corresponding to the right corner of the maze. And then finally, I know that since it's a vertex, I can do this dot def, and I will get the distance from start to finish. And since we're using CodeJudge, you have to do a print here. So let me just show you. If you look into the console to the right here, I have printed out this maze matrix, which is the way I load in the matrix. And you can see here the input is, the first row is ABA, BA, B, and then 3 A's. And you see that the maze matrix becomes like so. So the first list contains, the elements from the first row in the maze, and so on, right? And this is really neat. So a lot of talking. I'm sorry, it may be a little bit confusing, but as I mentioned, you do it in 3 steps. You create a graph, you do the BFS, and you put everything together. And now Sina had a question, which is, what do you mean by def? Well, you can think of def as the distance to a node. So like we had in a previous exercise, I think it was this one over